The universe contains places where physics itself breaks down completely. We are about to explore 30 cosmic locations where the established rules of reality simply stop working. By the end, you will gain a transformed perspective on the fabric of existence. How can a point of infinite density exist within a black hole? And what mysterious force is ripping the cosmos apart at an ever-increasing rate? What does it truly mean when our most fundamental science reaches its absolute limit? The universe operates on a set of rules so reliable we often take them for granted. These are the fundamental laws of physics, the invisible framework that gives our cosmos its order and predictability. They are the reason an apple falls straight down from a tree and why the planets trace graceful, repeating orbits around the sun. Giants of science, from Isaac Newton, who defined the force of gravity, to Albert Einstein, who revealed that gravity is actually the warping of space-time itself, dedicated their lives to mapping this cosmic rulebook. Their equations allow us to predict eclipses with pinpoint accuracy and to send probes on billion-mile journeys to distant worlds. This consistent framework makes the universe knowable. Yet, this very consistency makes it all the more shocking when we finally peer into the cosmic extremes and find places where the rulebook we trust so completely is torn to shreds. The failure of physics in these realms is not a flaw in the laws themselves, but a powerful signal that our current understanding is merely a chapter in a much grander story. It is at these breaking points where prediction turns to paradox that we catch our first glimpse of the deeper truths lying just beyond our current scientific horizon. Our journey into cosmic chaos begins at the most infamous destination of all, the crushing heart of a black hole. Here, buried beneath the event horizon from which not even light can escape, lies a point of ultimate mystery. Physicists call it the singularity. Imagine taking the entire mass of a giant star, a body millions of miles across, and crushing it down into a single, infinitesimal point. The result is a place of infinite density, where the very concepts of space and time as we experience them cease to have any meaning. The equations of Einstein's general relativity, which so beautifully describe the warping of spacetime around a black hole, lead to this point and then simply give up. They return results of infinity, a clear signal in mathematics that you have reached a boundary where your theory no longer applies. The great Stephen Hawking noted that this is a place where the laws of science, as we have written them, simply break down. It is the ultimate endpoint of gravitational collapse, a one-way street that ends in a complete and utter failure of prediction. At the singularity, the two great pillars of modern physics, general relativity, which governs the very large, and quantum mechanics, which governs the very small, collide in a storm of conflicting rules. Neither framework can describe what truly happens in that point of infinite density, creating a fundamental impasse that challenges our most basic assumptions about reality. This is not a minor gap in our knowledge, it is a yawning chasm, forcing physicists to search for a deeper theory, a theory of quantum gravity that can finally make sense of the place where physics itself stops working. But the singularity is not the only place where our understanding falters. Just outside that point of infinite mystery lies a boundary so absolute it has become legendary in science, the event horizon. This is not a physical surface you could touch, but a mathematical point of no return, a spherical cage woven from gravity itself. At the event horizon, the pull of the black hole becomes so intense that the escape velocity, the speed you would need to achieve to break free, exceeds the speed of light. And since nothing in the universe can travel faster than light, nothing that crosses this threshold can ever come back out. the consequences of crossing this line are bizarre beyond belief. From the perspective of someone watching from a safe distance, a spacecraft falling toward a black hole would appear to slow down as it approached the event horizon. Its clock would seem to tick more and more slowly, its light stretching into longer, redder wavelengths until the ship simply fades from view, frozen in time for all eternity. For those outside, it would take an infinite amount of time for the ship to actually cross the horizon. Yet, for the astronauts on board, time would pass normally. They would cross the boundary without any dramatic shudder, completely unaware of the moment they passed the point of no return, only to be immediately torn apart by the black hole's immense gravitational forces. This is the paradox of the event horizon, a place where a single event crossing a line happens in a finite time for one observer and takes forever for another. It completely scrambles our common sense understanding of cause and effect. This leads to one of the most vexing puzzles in all of physics, the black hole information paradox. The laws of quantum mechanics state that information about an object, the specific arrangement of all its particles, can never be truly destroyed. But if an object falls into a black hole and that black hole eventually evaporates, as Stephen Hawking theorized, what happens to all that information? Is it lost forever, violating a fundamental law of the universe, or is it somehow encoded on the event horizon itself, a cosmic scratchpad preserving the history of everything that ever fell in? The event horizon is not just a barrier in space, it is a barrier for our knowledge, a stark reminder that our most cherished rules of reality face their ultimate test at the edge of a black hole. Yet even the profound enigmas of black holes are overshadowed by a mystery that lies at the very beginning of everything. To find the third place where physics stops working, we must rewind the cosmic clock all the way back to time zero, the very first moment of the Big Bang. This was not an explosion in space, but the sudden, violent emergence of space and time themselves. In that initial, incomprehensibly brief sliver of time, known as the Planck epoch, the entire observable universe was compressed into a volume trillions of times smaller than a single atom. The density and temperature were not just high, they were infinite. Our most trusted theories of physics, the very tools we use to understand the cosmos, dissolve into gibberish under these conditions. General relativity, which describes the large-scale structure of the cosmos, and quantum mechanics, which governs the tiny subatomic world, both return nonsensical answers of infinity. They cannot describe a state where all the mass and energy of the universe occupies a single point. During this fleeting epoch, the four fundamental forces of nature, gravity, electromagnetism, and the strong and weak nuclear forces, were not separate. They were fused together into a single primordial superforce, a state of ultimate symmetry that we cannot replicate or fully comprehend. The very ideas of here and there, of before and after, had no meaning. Space and time as we know them did not yet exist. They were born in that instant, emerging from a state that is, by definition, indescribable. This is the ultimate origin point, a singularity that makes the one inside a black hole seem almost mundane by comparison. It is the one event that truly questions our understanding of something coming from nothing. Cosmologists are therefore forced to look beyond our current rulebook, developing new models like string theory or cosmic inflation, not to describe the moment of creation itself, but to describe the first moments after it, when physics as we know it began to stutter into existence. The Big Bang Singularity remains the ultimate barrier, the one place where our quest for origins runs headlong into a wall of infinite mystery. Leaving the violent birth of the cosmos behind, we find another theoretical rupture in the fabric of reality, one that promises shortcuts across the universe but delivers profound paradoxes instead. These are wormholes, hypothetical tunnels weaving through the folded layers of spacetime itself. Imagine the universe as a vast sheet of paper. If you wanted to travel from one edge to the other, the normal route would be a long journey across its entire surface. A wormhole offers a different path, a theoretical bridge that punches a hole through the paper, connecting two distant points with a shortcut that could span billions of light years in an instant. These cosmic passageways are not just science fiction, they are valid, if highly speculative, mathematical solutions to Einstein's field equations of general relativity. The equations allow for their existence, but the universe seems to have other ideas. The moment you try to build a stable, traversable wormhole, one a person could actually walk through, physics throws up an insurmountable barrier. The tunnel would want to collapse into a singularity instantly, crushing any potential traveler into non-existence. To prop it open, to create a stable gateway, you would need a truly bizarre substance, something known as exotic matter. This isn't just matter that is strange or unknown, it is matter that possesses a negative energy density. It would have to gravitationally repel rather than attract, something we have never observed in the known universe. Theoretical physicist Kip Thorne's work showed that maintaining such a structure would require a violation of a fundamental principle in general relativity called the averaged null energy condition. In simpler terms, it would demand that the very stuff holding the wormhole open must defy the normal, attractive pull of gravity that every other form of matter and energy in the cosmos obeys. This alone places wormholes firmly in the realm where our known laws break down, but the problems only deepen from there. If a wormhole could exist, it would not just be a tunnel through space, but a tunnel through time as well. By moving one end of the wormhole at relativistic speeds or placing it near a strong gravitational field, you could create a scenario where time passes at different rates for each mouth. Step in one end, and you could potentially step out the other end, not just in a different place, but in a different time, perhaps even in your own past. This immediately introduces the specter of time travel paradoxes. What happens if you travel back and prevent your own birth? The logical inconsistency is total, defying any coherent sequence of cause and effect. Wormholes, therefore, represent a double failure of physics as we know it. They first demand a substance that breaks the rules of general relativity to exist at all, and then, by their very nature, they threaten to shatter the logical foundation of causality itself. They exist in a precarious gray area, a mathematical possibility that our physical universe seems to explicitly forbid, pushing us to consider what dramatic revisions to our rulebook would be necessary to make such cosmic bridges a reality. The mechanism that drove this explosive growth presents a puzzle of its own. In the first fleeting fraction of a second after the Big Bang, the universe is theorized to have undergone a period of unimaginably rapid expansion known as cosmic inflation. Think of it like this: you are blowing up a balloon, but for one breathtaking instant, that balloon expands faster than the speed of light, smoothing and flattening its entire surface in a cosmic blink. This idea elegantly explains why the universe appears so uniform in all directions, but the engine behind this incredible event remains entirely unknown. What force could possibly cause spacetime itself to stretch at such a phenomenal rate? Physicists propose the existence of an inflationary field, a strange kind of energy that permeated the newborn cosmos. This field would have operated under such extreme energy conditions that the tiny, probabilistic rules of the quantum world would have completely overwhelmed the force of gravity. In this bizarre regime, particles would flicker in and out of existence, and the very fabric of space would have been a foaming, turbulent sea. Our standard model of physics, which keeps gravity and quantum mechanics in separate boxes, offers only incomplete, contradictory answers for what happened here. The energy scales involved were so immense they approach the Planck scale, the ultimate limit where the very concepts of space and time are thought to dissolve into a quantum foam. It is a realm where our current rulebook is not just inadequate, it is entirely mute. Even the brilliant physicist Roger Penrose has pointedly questioned whether inflation truly resolves the cosmic puzzles it was meant to, or if it simply papers over deeper gaps in our fundamental knowledge. To truly understand the first moment of creation, we need a theory that can seamlessly unite the vast and the infinitesimal, a theory of quantum gravity that remains one of the most elusive goals in all of science. The inflationary epoch stands as a profound reminder that our most successful cosmic stories are still built upon a foundation we do not yet fully comprehend. The crushing density of a neutron star's heart presents a different kind of failure, one where matter itself surrenders to forces beyond its design. These stellar corpses are the remnants of massive stars that have exploded and collapsed, squeezing more than the mass of our entire sun into a sphere no wider than a city. The pressure is so immense that atoms themselves are utterly destroyed. Electrons are crushed into protons, transforming them into neutrons, and the entire star becomes a single, city-sized atomic nucleus of unimaginable density. But even this bizarre state is just the surface of the mystery. As we push deeper toward the core, the conditions become so extreme that our knowledge reaches its absolute limit. Here, the neutrons themselves may break down under the overwhelming pressure. The familiar rules governing the strong nuclear force, the very glue that holds atomic nuclei together, begin to falter under this incredible strain. What happens when you pack matter this tightly is a question that cannot be answered in any laboratory on Earth. We simply cannot recreate such phenomenal densities. This means physicists cannot determine the true equation of state for matter at the center of a neutron star. Is the core a superfluid of free-flowing neutrons, a perfect liquid with zero viscosity? Or does the pressure become so great that the neutrons themselves shatter, their constituent parts, the quarks and gluons, spilling out to form a strange, exotic soup known as quark matter? Some theories even suggest the formation of stable strange matter, a bizarre state that could be the true, most stable form of matter in the universe, a possibility that is both thrilling and terrifying. These cosmic laboratories force us to confront the fact that matter can exist in states we have no names for, governed by rules we have not yet written. The very center of a neutron star is a sealed vault, hiding the final, secret behavior of matter under the most extreme conditions the universe can devise. Yet even the crushing density of a neutron star pales in comparison to the chaos churning in the void itself. The seventh place where physics stops working is the vacuum of empty space. Classical intuition tells us that a perfect vacuum is a true nothingness, a void completely devoid of substance, but the quantum world reveals a far stranger reality. What we perceive as empty is in fact a seething, bubbling cauldron of activity. At the tiniest scales, the vacuum is alive with virtual particles. These are not particles in the ordinary sense, but fleeting pairs of matter and antimatter that spontaneously blink into existence, borrowing energy from the universe for an impossibly brief moment before annihilating each other and vanishing back into the nothingness from which they came. This ceaseless, frantic dance is permitted by Heisenberg's uncertainty principle, a cornerstone of quantum mechanics which states that for brief instants, energy conservation can be temporarily violated. The very fabric of reality is not smooth and continuous, but a churning quantum foam, as physicist John Wheeler poetically described it. At the unimaginably small Planck scale, the very concepts of here and there, of before and after, may dissolve entirely. Space-time itself might not be a smooth sheet, but a foamy, discrete landscape where the smooth continuum predicted by Einstein's general relativity shatters into a probabilistic frenzy. This is not just a theoretical idea. We can witness the effects of this quantum turmoil in a laboratory. The Casimir Effect demonstrates this beautifully. When two incredibly smooth, uncharged metal plates are placed extremely close together in a vacuum, they are pushed together by a mysterious, invisible force. What is happening is that the seething sea of virtual particles exists in all possible wavelengths outside the plates, but in the narrow gap between the plates, only certain wavelengths can fit. This creates a pressure imbalance with more virtual particles pushing on the plates from the outside than from the inside, forcing them together. The void itself is pushing them. This measurable force is direct proof that empty space is not empty at all, but brimming with a fundamental energy that challenges our most basic notions of nothingness. The quantum vacuum is not a passive backdrop for the universe, but an active participant, a foundational layer of reality where our classical understanding of space completely and utterly breaks down. This paradox strikes at the very heart of physics, forcing a choice between two of our most cherished principles. On one side stands quantum mechanics, which holds the law of unitarity as sacred. This is the unbreakable rule that information, the complete quantum description of every particle, can never be truly destroyed. You can burn a book, scattering its ashes to the wind, but in principle, a being with perfect knowledge could collect every ash and wisp of smoke to reconstruct every single word. The information is scrambled, but it is never erased from the universe. On the other side stands general relativity, which seems to present the ultimate information shredder, the black hole. When an object crosses the event horizon, it vanishes from our universe, taking all its quantum information with it. For decades, physicists assumed this information was simply locked away forever inside the black hole, a cosmic vault that, while inaccessible, did not technically violate the quantum rule. But then Stephen Hawking made a discovery that turned this comfortable assumption into a full-blown crisis. He realized that black holes are not completely black. Due to those same quantum fluctuations in the vacuum we just explored, pairs of virtual particles can pop into existence right at the edge of the event horizon. In a devastatingly elegant trick of nature, one particle falls in while its partner escapes, carrying away a tiny bit of the black hole's energy. This is Hawking radiation, a faint whisper of heat that causes the black hole to slowly, over eons, evaporate until it vanishes completely. And here lies the catastrophic catch. The Hawking radiation that escapes is purely thermal. It is random noise, completely devoid of any information about what fell in. So, if the black hole evaporates into nothing but this featureless radiation, what happened to the original quantum information of the star, the book, or the astronaut that formed it? According to quantum mechanics, it must be preserved. According to Hawking's calculation, it is irrevocably lost. This is the information paradox, a direct and brutal contradiction. One of our two foundational theories must be wrong. To resolve this, physicists have been forced to propose solutions that sound like they are pulled from science fiction. One radical idea is the firewall hypothesis. It suggests that the event horizon is not a peaceful boundary after all, but a blazing wall of energetic particles that would instantly incinerate anything crossing it. This would preserve information by stopping anything from actually falling in, but it shatters Einstein's principle of equivalence, the core idea that falling into a black hole should be an uneventful journey, at least until the tidal forces rip you apart. Another, perhaps even more profound, solution is the holographic principle. This mind-bending concept proposes that all the information describing a three-dimensional volume of space, like the interior of a black hole, can be entirely encoded on its two-dimensional boundary, the event horizon. It is as if the entire rich, three-dimensional reality we experience is merely a projection from information stored on a distant, flat surface, like a cosmic hologram. If this is true, then the information of what falls into the black hole is not lost inside, but is smeared and stored on the event horizon itself, eventually leaking back out in the Hawking radiation. This would preserve the information, but it forces us to abandon our most intuitive sense of locality, the idea that objects and information exist in a specific place. The information paradox is more than a technical puzzle. It is a glaring signpost pointing toward a deeper layer of reality, one where space and information might be fundamentally intertwined in ways we are only beginning to imagine. While the quantum vacuum churns with hidden energy, a far more substantial mystery dominates the cosmos on the grandest scales. Dark matter is the universe's silent partner, an invisible presence that holds galaxies together and sculpts the largest structures in existence. We know it is there because we can see its gravitational hand at work. Stars on the outer rims of spiral galaxies orbit at speeds that should fling them into the intergalactic void, yet something with immense mass, something we cannot see, provides the extra gravitational glue to keep them from flying apart. This mysterious substance makes up roughly 27% of all the mass and energy in the cosmos, nearly 6 times the amount of all the normal, visible matter that makes up every star, planet, and person. But what is it? We have no idea. It does not emit, absorb, or reflect any form of light. It is completely transparent to the entire electromagnetic spectrum, from radio waves to gamma rays. It simply does not interact with light in any way, making it utterly invisible to our telescopes. This fundamental property means it cannot be composed of any of the particles described in the incredibly successful Standard Model of particle physics. Protons, neutrons, electrons, none of the known building blocks of our world can account for it. For decades, the leading theoretical candidate has been a class of particles known as WIMP, or weakly interacting massive particles. The hypothesis was elegant. These particles would interact only through gravity and perhaps the weak nuclear force, making them nearly impossible to detect directly. Physicists built incredibly sensitive experiments deep underground, in old mines and beneath mountains, shielding them from cosmic rays in the hope of catching the faintest bump from a WIMP collision. Yet, after years of searching with ever more sensitive detectors, they have found nothing. The silence from these experiments is deafening, forcing a profound re-evaluation of what dark matter could be. Perhaps the most visually striking evidence comes from observations of cosmic collisions, like the Bullet Cluster. This is a system of 2 galaxy clusters that have smashed right through each other. The normal, visible matter in the clusters, mostly in the form of hot, X-ray emitting gas, was slowed down and dragged by friction during the collision. But the dark matter, inferred by its gravitational lensing of background light, sailed right through the crash completely unaffected. It became separated from the normal matter, leaving a ghostly halo of mass surrounding the visible galaxies. This observation delivers a devastating blow to theories that try to explain away dark matter by simply modifying the laws of gravity. Modified gravity cannot easily explain why the gravitational effect would become physically separated from the visible matter itself. So we are left with a staggering conclusion. The vast majority of the matter in the universe is made of something that is fundamentally alien to everything we have ever seen, touched, or measured. It is a substance that governs the fate of galaxies, yet passes through our planet, our homes, and even our bodies, billions of these phantom particles every second without a trace. Dark matter is not a minor puzzle. It is a monumental failure of our standard model of physics, a silent testament to the fact that we are still blind to most of the material reality that makes up our cosmos. If dark matter is the silent giant holding the cosmos together, dark energy is the phantom force tearing it apart on the grandest stage imaginable. While dark matter's gravity pulls, dark energy pushes, and it is winning the cosmic tug of war. This mysterious component makes up a staggering 68% of the entire energy budget of the universe. It is the dominant player in the cosmos, and we have almost no idea what it is. Its primary effect is both simple and utterly bizarre. It is causing the expansion of the universe to accelerate. Think of the Big Bang as a single, colossal explosion sending galaxies flying outward. Everyone expected that the mutual gravitational pull of all that matter would act like a brake, gradually slowing this cosmic expansion over billions of years. But observations of distant supernova in the late 1990s revealed the shocking truth. The expansion is not slowing down at all, it is speeding up. Galaxies are not just coasting away from each other, they are fleeing from one another at faster and faster rates, as if space itself is being stretched by some invisible, repulsive force. This force behaves like a negative pressure woven into the very fabric of the vacuum. While all known forms of matter and energy create an attractive gravitational pull, dark energy generates a kind of gravitational repulsion. It is as if empty space itself is endowed with an anti-gravity effect, and as the universe expands and creates more space, this repulsive force only grows stronger, leading to a runaway acceleration. The most straightforward explanation for this bizarre behavior comes from an old idea of Albert Einstein's, the cosmological constant. Originally, he introduced this term into his equations as a fudge factor to achieve a static universe, a concept he later called his greatest blunder. But with the discovery of the accelerating expansion, the cosmological constant was resurrected. It represents a constant energy density inherent to the vacuum of space itself. The problem is one of the most spectacular failures of prediction in the history of science. When physicists attempt to calculate the expected value of this vacuum energy using quantum field theory, the result is a number that is too large. It is not just a little off. The theoretical calculation exceeds the observed value by a factor of 1 followed by 120 zeros. This is not a small discrepancy. It is the largest mismatch between theory and experiment ever recorded. It is a clear and deafening signal that our understanding of the quantum vacuum and its interplay with gravity is profoundly, fundamentally wrong. In response to this colossal failure, other theories have emerged, such as quintessence. This model proposes that dark energy is not a constant, but a dynamic field that changes over time, a kind of fifth fundamental force. Yet, even these ideas remain speculative, unable to pin down the true nature of this cosmic driver. Dark energy is more than just a puzzle. It is the central mystery of modern cosmology. It dictates the ultimate fate of the entire universe, pointing toward a cold, dark, and empty end where galaxies vanish over the cosmic horizon. The fact that we can name the force that controls the destiny of everything, yet cannot explain it, stands as a humbling testament to the limits of our current physics. A quantum particle does not choose its state until you force it to make a decision. This is the bizarre heart of the quantum measurement problem, a fundamental schism in reality that occurs at the smallest of scales. In the quantum realm, particles like electrons exist in a ghostly state of superposition, meaning they can be in multiple places or possess multiple properties simultaneously. An electron is not simply here or there. It is a blur of probabilities, a wave of potential outcomes described by its wave function. The mathematics is precise and beautiful, but it describes a world of pure possibility. The crisis arises the moment we try to look. When a physicist sets up a detector to measure the particle's position, this fuzzy cloud of potential abruptly snaps into a single, definite reality. The wave function is said to collapse. The particle is suddenly, definitively in one place. But here is the profound mystery that physics cannot solve. What exactly constitutes a measurement? Is it the interaction with the detector? Is it the registration of the data? Or, most disturbingly, is it the moment a conscious mind becomes aware of the result? There is no agreed-upon physical process for this collapse, no equation that describes the transition from the many to the one. It is a line in the sand between the quantum world and our own classical reality, a line drawn by an unknown hand. Erwin Schrödinger crafted his famous cat thought experiment to expose the sheer absurdity of applying this quantum logic to the world we see. He imagined a cat sealed in a box with a radioactive atom, a Geiger counter, and a vial of poison. If the atom decays, the counter triggers, releasing the poison and killing the cat, according to the rules of quantum mechanics. Until someone opens the box and looks, the radioactive atom exists in a superposition of both decayed and not decayed. Therefore, the cat must also be in a superposition, both alive and dead at the same time, a grotesque and seemingly impossible state. Schrödinger was not proposing that cats could be undead. He was pointing a finger directly at the glaring flaw in the interpretation of his own theory. The puzzle forces us to ask, when does the superposition end? When does the universe decide? The Copenhagen interpretation, championed by Niels Bohr, offers one answer by simply stating that the act of observation by a classical instrument causes the collapse. But this feels deeply unsatisfying, as it defines the problem away by creating a special, unexplained category for measurement itself. In stark contrast, the many worlds interpretation boldly claims that the wave function never collapses at all. Instead, at the moment of measurement, reality splits into multiple branches. In one universe, you open the box to find a living cat, and in another, an entirely separate version of you finds a dead one. While this elegantly avoids the need for a collapse, it demands we accept the existence of an infinite, ever-branching multiverse, a staggering ontological price that can never be experimentally verified. Other interpretations, like de Broglie-Bohm pilot wave theory, suggest that particles have definite positions all along, guided by a hidden wave, while yet others propose that wave function collapse is a real physical process driven by gravity or continuous spontaneous localization. The fact that brilliant physicists can hold such wildly different views on the most basic process of reality, the transition from possibility to actuality, reveals a chasm in our understanding. The quantum measurement problem is not a minor technicality. It is a silent fault line running through the foundation of physics, forcing us to question whether our role as observers is passive, or if the very act of looking is what writes the script of the world. This cosmic uniformity presents a puzzle so profound it threatens to unravel our standard story of the Big Bang. Look in any direction, and the faint afterglow of creation, the cosmic microwave background, shows a nearly identical temperature. The entire sky is painted with a uniform frost just a few degrees above absolute zero. Yet, according to the standard model of cosmology, this should be impossible. The universe simply has not existed long enough for light or heat to have traveled from one side of the cosmos to the other. Distant regions on opposite sides of the sky have always been beyond each other's light cones, meaning they have never been in causal contact. It is as if you walked into a vast auditorium where thousands of people who have never met or spoken are all humming the exact same note in perfect unison. How could such perfect coordination occur without any communication? This is the horizon problem, a fundamental challenge to causality itself. For these regions to reach thermal equilibrium, information about temperature would have had to travel faster than the speed of light in the young universe, a clear violation of the established rules. One leading solution is the theory of cosmic inflation, which proposes that the entire observable universe was once a tiny, subatomic patch that was causally connected. Then, in an unimaginably brief burst of hyper-expansion, this tiny patch was stretched to a size larger than our entire visible cosmos, smoothing out all temperatures and densities in an instant. While this is an elegant fix, the inflationary field that supposedly drove this event remains entirely hypothetical and unverified. The horizon problem, therefore, is more than a minor inconsistency. It is a stark warning that our standard cosmic timeline is incomplete. It forces us to consider that the rules governing the universe's first moments may have been radically different from those we observe today, perhaps involving physics that allows for a deeper, faster connection across the fabric of spacetime than we currently understand. This ghostly connection between particles reveals the 13th place where physics stops working, a phenomenon so strange it troubled even Einstein. When two particles become quantumly entangled, they lose their individual identities, merging into a single, shared quantum state. Imagine creating a pair of electrons so deeply linked that their spins are perfectly correlated, one always pointing up when the other points down. Now take one of these entangled electrons on a journey to the farthest star, while its partner remains in a lab on Earth. The moment a scientist measures the particle on Earth and finds it spinning up, its distant twin, millions of light years away, instantly snaps into a state of spinning down. This change happens not at the speed of light, but seemingly in zero time, as if the space between them does not exist. Einstein derided this as spooky action at a distance because it appeared to violate the core principle of locality, the idea that nothing, not even information, can travel faster than light, and that objects are only influenced by their immediate surroundings. For decades, physicists hoped there might be a simpler, hidden explanation, perhaps that the particles were like a pair of gloves, with one always being left-handed and the other right-handed from the moment they were created. The universe, in this view, would just be revealing a pre-existing state, but the brilliant work of physicist John Stuart Bell provided a way to test this. His theorem set up a precise mathematical inequality that any universe governed by local hidden variables must obey. When physicists finally performed these delicate experiments, the results were unequivocal. The quantum particles violated Bell's inequality. They were not just revealing a hidden plan, they were genuinely communicating in a way that is fundamentally non-local. This means the connection between them is instantaneous and does not depend on any signal traveling through the space that separates them. The universe, at its most fundamental level, appears to be woven together with threads that ignore the distance we perceive. This quantum interconnectedness forces us to confront a reality where separation may be an illusion, a temporary condition of our classical world that dissolves entirely in the quantum realm. It suggests a cosmos that is profoundly whole, where every part is intimately linked to every other part in a way that our current physics can describe with equations, but cannot truly explain. This quantum interconnectedness hints at a deeper, more chaotic layer of reality beneath the subatomic world. There exists a fundamental limit to how small we can probe, a final frontier where the very idea of a smooth, continuous universe shatters into a storm of pure chaos. This is the Planck scale, a realm so inconceivably tiny that all our familiar concepts of space and time dissolve into nonsense. At this scale, a distance of 10 to the negative 35th meters, the quantum fluctuations of the vacuum become so violent and energetic that they overwhelm the fabric of spacetime itself. The smooth, geometric canvas described by Einstein's general relativity cannot survive here. It is like looking at the surface of a calm pond with a microscope of infinite power, only to discover that what seemed smooth is actually a seething, frothing foam of bubbles, each one a tiny universe popping in and out of existence. In this foam, the very ideas of here and there, of before and after, cease to have any stable meaning. You cannot measure a distance smaller than the Planck length, nor a duration shorter than the Planck time, because the energy required to make such a measurement would be so immense it would collapse into a tiny black hole, destroying the very region you are trying to observe. This is the ultimate limit of measurement, a point where our most successful theories of physics, quantum mechanics, and general relativity enter a war of attrition. Each theory insists on its own rules, and together they produce impossible answers, predicting infinite probabilities and infinite curvatures. The smooth spacetime of relativity and the discrete probabilities of quantum mechanics cannot coexist here, revealing their fundamental incompatibility. In an attempt to describe this chaotic frontier, physicists have proposed radical new frameworks. String theory suggests that the fundamental constituents of reality are not point-like particles, but tiny, vibrating loops of energy. In this view, the apparent chaos of the Planck scale is the result of an unimaginably complex symphony of these strings. Loop quantum gravity, another approach, proposes that space itself is not continuous, but is woven from a fabric of finite, interlocking loops, a spin network that gives space a discrete, atomic structure. Yet, for all their mathematical elegance, these theories currently reside in a purgatory of speculation. The energies required to probe the Planck scale are over a quadrillion times greater than what our most powerful particle colliders can produce. We are like astronomers trying to map a distant galaxy with a pair of binoculars, knowing a magnificent truth lies just beyond our grasp. The Planck realm is the ultimate horizon of our knowledge, a place where physics as we know it does not just stop working. It ceases to be a coherent language altogether, forcing us to dream of an entirely new vocabulary for reality. While black holes devour everything in their path, their theoretical opposites offer an even greater affront to cosmic order. White holes are imagined as the exact time reversal of black holes, cosmic fountains that endlessly pour matter and energy back into the universe while violently rejecting any attempt to enter. If you were to somehow approach one, it would be like trying to swim up a waterfall moving at the speed of light. No force in the universe could push you past its impenetrable boundary. These bizarre objects are not just science fiction. They emerge as valid mathematical solutions from the very same equations of general relativity that predict black holes. They represent a universe running in reverse, a region where gravity becomes a fundamentally repulsive force, spewing out everything from singularities we cannot see. The problem is that this beautiful mathematical symmetry creates catastrophic physical paradoxes. A white hole would fundamentally violate the second law of thermodynamics, the unbreakable rule that disorder or entropy always increases in the universe. A white hole would be a cosmic engine of order, taking the chaotic jumble of matter and energy that fell into a black hole and ejecting it in a structured, organized stream, effectively causing the total entropy of the universe to decrease. This is as likely as a shattered glass spontaneously reassembling itself and leaping back onto a table. The existence of a white hole would require time's arrow to run backwards within its domain, creating a pocket of reality where cause and effect are inverted. You would see events unfold where the effect precedes the cause, a universe where a ripple in a pond would converge to drop a stone into the water. This completely unravels our understanding of causality. For this reason, most physicists consider white holes to be mathematically possible but physically impossible, a ghost in the machine of general relativity that the universe itself seems to reject. Yet their theoretical shadow forces us to ask a profound question. Why does time have a preferred direction at all? The laws of physics themselves are almost entirely time-symmetric. They work just as well running forwards or backwards. But our lived experience of time is a one-way street. White holes highlight this deepest of mysteries, the origin of time's arrow, by presenting us with a vision of a cosmos where it simply does not apply. Even as we grapple with the fundamental laws of the quantum world, a colossal force is tugging at our entire galactic neighborhood from the depths of intergalactic space. This is the Great Attractor, a gravitational anomaly of such immense power that it is pulling our Milky Way, along with thousands of other galaxies, toward a specific point in the cosmos. We are all caught in a silent, cosmic river, flowing toward a destination we cannot clearly see. The pull originates from the general direction of the Centaurus constellation, but its true heart lies hidden behind a thick veil of cosmic dust and countless stars at the core of our own galaxy. This obscured band of the sky is known to astronomers as the Zone of Avoidance, and it acts like a giant blind spot, preventing our telescopes from directly observing the source of this immense gravitational pull. We can feel its influence, a relentless tug on the motion of galaxies across hundreds of millions of light years, but we cannot look directly at it. The mystery deepens when we calculate the mass required to generate such a powerful flow. The visible mass we can detect in that region, the sum of all the galaxies and clusters we can peer around the obscuring dust, is simply not enough to account for the observed gravitational force. It is as if you felt a powerful current in the ocean, but when you looked down, you saw only a gentle slope on the seafloor, utterly insufficient to explain the water's rush. This leaves physicists with two deeply puzzling possibilities. Either there is a staggering amount of unseen mass, a hidden concentration of dark matter so vast it defies our current models of cosmic structure, or our understanding of gravity itself, Einstein's general relativity, begins to fray at these immense intergalactic scales. The Great Attractor is not just a point in space, it is a profound question mark. It forces us to admit that even as we map the large-scale structure of the universe, we might be missing the most massive features entirely, or that the force that binds the cosmos operates by rules we have not yet fully deciphered. Just when we thought the cosmos was a grand, featureless expanse, a ghostly pattern emerges from the afterglow of creation itself. The cosmic microwave background, that ancient light from the infancy of the universe, holds a secret it was never supposed to reveal. Scattered across this fossilized radiation is a series of unexpected alignments, a strange correlation that seems to point back toward us. Scientists have given this bizarre phenomenon a dramatic nickname, the axis of evil. It suggests that the largest structures in the universe, the very ripples from the Big Bang, might be subtly aligned with the plane of our own solar system. This is not just a minor statistical quirk, it is a direct challenge to one of the most sacred principles in all of cosmology. The cosmological principle states that the universe, when viewed on a sufficiently large scale, should look the same in every direction and from every location. There should be no special place, no center, and certainly no preferred axis that aligns with our local neighborhood. The cosmos is supposed to be isotropic and homogeneous, a vast, featureless sea of galaxies. The axis of evil anomaly whispers that this might not be entirely true. It hints that we might, against all odds, be sitting in a location with a privileged view, a notion that modern cosmology has spent centuries trying to eradicate. Could it be a colossal coincidence, a statistical fluke in the data? Researchers have checked and rechecked the measurements from multiple satellites, from COBE to W map to Planck, and the strange alignments persist. The probability that this pattern arose purely by chance is incredibly small, forcing physicists to consider far more radical explanations. Perhaps our understanding of the universe's large-scale structure is fundamentally incomplete. Maybe there is a flaw in our models of cosmic inflation, the process that supposedly set up these initial conditions. Or, most thrillingly, this could be a fingerprint of entirely new physics, a phenomenon that connects the unimaginably large scale of the cosmos with our own local celestial backyard. If this alignment is real, it would mean that the universe has a subtle grain to it, a preferred direction woven into the fabric of space-time on the grandest of scales. Confirming the axis of evil would not just add a new chapter to cosmology, it would force us to burn the old one and start anew. Even the most meticulously planned journeys can reveal hidden surprises. For decades, two robotic pioneers, the Pioneer 10 and Pioneer 11 spacecraft, sailed through the silent expanse of the outer solar system. They were humanity's first emissaries to the giant planets, and their trajectories were calculated with an astronomer's precision, governed by the clockwork certainty of Newton's and Einstein's laws. Yet, as they ventured farther from the sun, a faint, persistent whisper of a problem began to emerge. Tracking data revealed that both spacecraft were experiencing a tiny, unexplained deceleration, a constant, minuscule tug back toward the inner solar system. This was the Pioneer Anomaly, a deviation so small it was like a single extra grain of sand slowing a rolling boulder, but it was undeniably there, and it defied all immediate explanation. For years, this ghostly signal haunted physicists. Was it a sign of some unknown physical effect, a subtle flaw in our understanding of gravity itself at the fringes of our own cosmic neighborhood? Could it be evidence of dark matter exerting a slight drag, or perhaps a hint that Einstein's theory of general relativity needed a tiny adjustment over vast interplanetary distances? The anomaly became a focal point for those searching for cracks in the established pillars of physics, a puzzle that seemed to suggest our rulebook was incomplete even in the well-mapped realms close to home. The eventual solution, however, was a masterclass in scientific humility. After years of painstaking analysis, a team of researchers determined that the culprit was not new physics, but something far more mundane, though incredibly difficult to model. The slight braking force was caused by the spacecraft's own heat. The plutonium in their power generators produced a steady stream of warmth, and this thermal radiation was escaping the probes asymmetrically. It was not pushing them like a rocket, but the tiny photons of heat carrying momentum were acting like a faint, constant breeze on a microscopic sail, providing just enough thrust in the opposite direction to create the observed deceleration. The Pioneer Anomaly was closed, but its legacy is profound. It stands as a powerful testament to the importance of precision and the relentless pursuit of even the smallest discrepancies. For years, this tiny signal challenged our confidence and forced a deep re-examination of the forces we thought we knew. It reminds us that our understanding of the universe is built not just on grand theories, but on our ability to measure, to question, and to accept that sometimes the most intriguing mysteries are solved not by rewriting the laws of physics, but by looking more closely at the intricate details we had previously overlooked. The silent ballet of interplanetary travel holds its own subtle mystery. For decades, we have used the gravity of planets like cosmic slingshots, a technique called a gravitational assist that expertly propels our spacecraft deeper into the solar system. The physics of this maneuver is considered a solved problem, a perfect demonstration of orbital mechanics in action. Yet, during these precise Earth flybys, something peculiar has occurred. Multiple spacecraft, including the Rosetta mission bound for a comet and the Galileo probe sent to Jupiter, have experienced tiny, unexpected changes in their velocity. The deviations are minuscule, mere millimeters per second, but they are undeniably there, and they are consistent. Each time one of these spacecraft swung around our planet, tracking data revealed a speed that was slightly different from what our most careful calculations predicted. It is as if an unseen hand gave the probe a gentle, inexplicable nudge. The immediate suspicion, of course, is some form of measurement error or an unaccounted-for effect from the Earth's atmosphere or its complex gravitational field. Yet, after exhaustive analysis, no conventional explanation has been able to fully erase the discrepancy. This is the Flyby Anomaly, a ghost in the machine of celestial navigation. In response, physicists have been forced to consider far more radical ideas. Could a halo of unconventional dark matter surrounding Earth be imparting this tiny drag or boost? Or does this suggest that Einstein's theory of general relativity, while spectacularly successful on larger scales, requires a subtle modification when dealing with the high-speed, rotating reference frames of a planetary flyby? Perhaps the rotation of Earth's mass itself generates a faint, previously unknown gravitational effect that our equations simply miss. None of these proposals have gained universal acceptance, leaving the anomaly as an open question. It serves as a humbling reminder that even here, within our own celestial backyard, the application of our most trusted physical laws can reveal a faint crack. The Flyby Anomaly proves that sometimes the most profound mysteries are not found in the hearts of black holes or the depths of deep space, but in the quiet, unexplained whisper of a spacecraft speeding past our own world. Far from the dense crowds of galaxies, the cosmos holds its emptiest places. These are the cosmic voids, unimaginably vast regions of near-nothingness that stretch for hundreds of millions of light-years. If the universe's structure is a cosmic web with galaxies clustered along great filaments like pearls on a string, then the voids are the gaping, empty spaces between those threads. Inside one of these voids, you could travel for a lifetime across a volume encompassing millions of galaxies and find almost nothing at all. The density of matter here is so exceptionally low that these regions are often thousands of times emptier than the cosmic average. This profound emptiness creates a unique environment where the very expansion of the universe behaves differently. In the crowded galactic cities, gravity acts as a brake, relentlessly pulling matter together and slowing down the local expansion of space. But inside a void with so little matter to hold it back, the expansion proceeds almost unchecked. It is as if dark energy, the mysterious force driving cosmic acceleration, finds its purest expression here, stretching the emptiness faster than the rest of the cosmos. This creates a fascinating dynamic, a universe expanding at different rates in different places, challenging our simplified models of a uniformly growing cosmos. The evolution of these voids themselves presents a major puzzle for cosmologists. According to our standard models of structure formation, the tiny fluctuations in the early universe should have grown under gravity to create both the dense clusters and the empty voids we see today. But the observed properties of the largest voids, their shapes, their sharp boundaries, and the peculiar motions of the few galaxies within them, do not always match the simulations. The dynamics seem off, Some theoretical physicists now speculate that the behavior of these vast emptinesses might be a clue that our theory of gravity, Einstein's general relativity, needs revision on the largest scales. Perhaps an alternative theory, like modified Newtonian dynamics or something even more radical, could better explain why these voids evolve the way they do. The cosmic void is more than just an empty spot on the map. It is a controlled experiment in nothingness, a place where the subtle tug of war between gravity and dark energy plays out in its most extreme form, revealing yet another frontier where our established physics meets an observational challenge it cannot fully resolve. The vast emptiness of cosmic voids finds a strange echo much closer to home, in the frozen outskirts of our own solar system. Far beyond the orbit of Neptune, the Kuiper belt stretches out like a distant ring of icy debris, a relic from the solar system's violent birth. This is the domain of dwarf planets like Pluto, a region teeming with frozen worlds and ancient planetesimals that never coalesced into a larger planet. For billions of miles, this belt continues, its population of objects slowly thinning out as you travel farther from the Sun. But then, at a distance of approximately 50 astronomical units, something bizarre happens. The bottom drops out. The number of detectable objects doesn't just continue its gradual decline, it plummets off a cliff. This is the Kuiper Cliff, a sudden and dramatic boundary where the expected population of icy bodies virtually vanishes. It's as if you were walking through a forest that grew progressively thinner, only to step across an invisible line into a barren desert. Our leading models of solar system formation, which have so successfully explained the architecture of the inner planets and the asteroid belt, predict no such sharp edge. The disk of primordial material from which the planets formed should have faded away gradually, leaving behind a Kuiper belt that slowly diminishes in density over a much greater distance. The cliff is a stark contradiction, a clear sign that our story of how the solar system ended is missing a crucial chapter. What could have carved out this void? One tantalizing possibility is the gravitational hand of an unseen planet, a so-called Planet 9 lurking in the profound darkness far beyond the cliff. This hypothetical world, with a mass several times that of Earth, could have shepherded the outer solar system, its immense gravity either clearing out the region beyond 50 astronomical units or preventing objects from forming there in the first place. Yet, despite extensive searches, no such planet has been conclusively found. Other theories suggest our solar system's birth cloud was truncated by a close encounter with a passing star in its infancy, violently stripping away the outer material. Or perhaps the objects beyond the cliff are simply too dark and distant for our current telescopes to see, though this seems unlikely given the abruptness of the drop-off. The Kuiper Cliff is more than a curiosity, it is a frontier. It stands as a quiet challenge to our planetary science, a reminder that even in our own celestial backyard, the final map remains unfinished, its edges marked by a mystery that our established rules cannot yet cross. The silent spin of a distant galaxy holds a secret that shattered our picture of the cosmos. When astronomers first measured how fast stars orbit within spiral galaxies like our own Milky Way, they expected to see a familiar pattern, a celestial carousel governed by the same laws that keep our planets in line. According to Kepler's laws and Newtonian gravity, stars closer to the galactic center, where most of the visible mass is concentrated, should whip around at high speeds. Stars farther out in the sparse galactic suburbs, feeling a weaker gravitational pull, should orbit much more slowly, just as Pluto trudges slowly around the Sun compared to the inner planets. Yet the observations revealed something completely different. The rotation curves, the graphs plotting orbital speed against distance from the center, did not fall. They stayed flat, Whether a star was relatively close to the bright galactic core or far out in the dim, dusty fringe, it was orbiting at nearly the same speed. This was as bizarre as finding that all the planets in our solar system, from Mercury to Neptune, circled the Sun at identical velocities. The visible galaxy alone, all its stars and glowing gas, simply did not contain enough mass to generate the gravity needed to hold these far-flung, fast-moving stars in their orbits. Without an immense amount of additional, unseen matter providing extra gravitational glue, these outer stars should have been flung off into the intergalactic void. This flat rotation curve phenomenon became the first direct, undeniable evidence for dark matter. It forced astronomers to conclude that every spiral galaxy is embedded within a gigantic, invisible halo of mass, a ghostly cocoon that holds the entire structure together. In response to this crisis, some physicists proposed a radical alternative. Perhaps our understanding of gravity itself was flawed on the scale of galaxies. This idea, known as modified Newtonian dynamics or MUND, suggests that the force of gravity behaves differently at extremely low accelerations, like those experienced in the outer reaches of a galaxy. It is a compelling idea that does away with the need for invisible matter, but it has its own struggles. While MUND can beautifully explain the rotation curves of many isolated galaxies, it has a much harder time accounting for the gravitational behavior seen in colossal cosmic collisions, like the Bullet Cluster, where the gravitational effects clearly separate from the visible matter. So we are left with a fundamental schism. Does the flat spin of a galaxy point to a universe filled with invisible, unknown particles, demanding a revolution in particle physics? Or does it mean that Isaac Newton and Albert Einstein, while correct in our solar system, were subtly wrong on the grand stage of a galaxy, demanding a revolution in our understanding of gravity itself? The gentle, constant whirl of stars in a distant pinwheel of light presents us with a choice between two equally profound upheavals in our understanding of the cosmos. The silent depths of space occasionally send a signal so startling it cuts through the background noise of the cosmos with unnerving clarity. On a quiet August night in 1977, the Big Ear radio telescope at Ohio State University recorded something that would become a permanent enigma. A volunteer astronomer named Jerry Amon was scanning printed data, a long scroll of numbers and letters representing the faint hiss of the universe, when his eye caught an anomaly so extraordinary he circled it in red pen and wrote a single, telling word beside it: "Wow." The signal was a powerful, narrowband radio burst, the kind theoretically predicted for an artificial transmission, and it lasted for a full 72 seconds. It came from the direction of the constellation Sagittarius, rising and then falling in intensity, exactly as you would expect from a distant source passing through the telescope's fixed field of view. Everything about its profile screamed intelligence, a focused beacon in a cosmos filled with the chaotic crackle of natural radio sources. Yet after that one brilliant shout, there was only silence. Astronomers have pointed every available instrument toward that patch of sky for decades, listening for a repeat, a follow-up, anything. They have heard nothing. The signal has never been replicated. Natural explanations have been proposed, of course. Perhaps it was a comet nobody knew about at the time, reflecting sunlight in just the right way, but the known comets in that region do not match the signal's origin. Maybe it was an unusual microlensing event, where a foreground object amplified a distant natural radio star for a brief moment, but the probability of such a perfect, isolated event is vanishingly small. None of these proposals fully account for the signal's unique combination of power, frequency, and brevity. The WOW signal sits in a liminal space, a boundary where conventional astrophysics runs out of convincing answers. It forces us to confront a profound possibility that we may have briefly intercepted a message not meant for us, a cosmic flare from a technology we cannot comprehend, or a natural phenomenon so rare we have only witnessed it once in all of human history. It is a ghost in the machine of astronomy, a single, perfect data point that refuses to be explained away, forever challenging our place in a universe that may be far noisier or far quieter than we ever dared to imagine. A split-second flash from a galaxy a billion light-years away can outshine an entire sun. These are fast radio bursts, cosmic screams that pack more energy than our sun emits in 80 years into a mere millisecond. They arrive without warning, a brilliant and fleeting spike in our radio telescopes, and then vanish back into the silence of deep space. Their origins are one of the most electrifying puzzles in modern astronomy. For a brief moment, these bursts become the most powerful radio sources in the entire universe, and we have almost no idea what creates them. We have managed to trace some of these signals back to their home galaxies, and in a few remarkable cases, we have even linked them to specific cosmic objects known as magnetars. These are neutron stars with magnetic fields so unimaginably powerful they could strip the information from every credit card on Earth from halfway across the galaxy. It seems logical that such a monstrous object could be the engine behind these bursts, yet this explanation only deepens the mystery. The sheer energy required for the most powerful fast radio bursts pushes far beyond what our current models of magnetar flares or colliding neutron stars can possibly produce. How can any natural process generate such an immense amount of power so quickly? The puzzle becomes even more bizarre when we discover that some of these bursts are not one-off cataclysms. They repeat. A single source in a distant galaxy can fire off multiple signals, sometimes in a predictable pattern, sometimes at random. This repeating nature completely shatters the model of a one-time, destructive event like a star collapsing or two black holes merging. You cannot have a stellar explosion happen again and again in the same spot. This forces theorists back to the drawing board, proposing engines like processing magnetars, which wobble like a spinning top and periodically send out beams of radiation, or interactions between neutron stars and their asteroid belts. But these are speculative fixes for a problem that challenges our fundamental understanding of energy and matter in the most extreme environments. These millisecond flashes are more than just cosmic fireworks. They are messengers from the farthest reaches of space and time, carrying encrypted information about physical laws operating under conditions we cannot hope to recreate. Each one that arrives is a stark reminder that our catalogue of cosmic disasters is still incomplete, hinting at celestial engines and perhaps even new physics we have not yet begun to dream of. The universe protects itself with an invisible shield, a theoretical limit on the most powerful particles racing through the void. Known as the GZK Cutoff, this cosmic speed limit is imposed by the ancient afterglow of the Big Bang itself. The idea is simple yet profound. Imagine the entire cosmos is filled with a faint, cold sea of microwave radiation, the leftover heat from creation. Now picture an atomic nucleus, a single proton from a distant galaxy, traveling through this sea at almost the speed of light, carrying more energy than a professionally thrown baseball. According to our best models, such an ultra-high-energy cosmic ray should not be able to travel very far. It should constantly collide with the photons of this cosmic background radiation. Each collision would be like a high-speed car crash, sapping the proton's energy bit by bit until it slows down below the theoretical cutoff. Over vast intergalactic distances, this process should act like a cosmic filter, preventing any particles from reaching Earth with energies beyond a certain calculable point. This is the rule, a firm prediction born from the well-tested laws of special relativity and particle physics. but the universe, it seems, loves to break its own rules. Our detectors on Earth have recorded the impossible, catching a handful of these cosmic cannonballs with energies far exceeding the GZK limit. These particles should not exist. They should have been slowed to a crawl by their long journey through the photon sea. Their very presence here is a direct contradiction, a paradox written in the most energetic handwriting nature can muster. So where do they come from? If these rays traveled from distant galaxies, our understanding of their journey is fundamentally flawed. Perhaps they come from incredibly violent but nearby sources within our own galactic neighborhood, cosmic accelerators of unimaginable power that we have yet to identify. Or, more thrillingly, their survival might require a rewrite of the physics textbooks. Maybe special relativity itself needs a tiny, high-energy adjustment. Or perhaps these particles are the decay products of exotic, super-heavy dark matter particles annihilating in the depths of space. The GZK paradox is not just a puzzle about particle origins. It is a direct challenge to our models of how matter and radiation interact across the largest empty spaces in the cosmos, forcing us to consider that the rules of the road for the universe's fastest travelers are not what we thought they were. A particle can face a wall it simply does not have the energy to climb, yet it appears on the other side as if the wall was never there. This is not science fiction, it is quantum tunneling, a daily reality for the subatomic world that powers the stars yet defies all classical intuition. In our everyday experience, if you roll a ball toward a hill, it will only reach the top if you give it enough energy to get over the crest. If it does not have that energy, it rolls back down. This is the unbreakable rule of classical physics, but in the quantum realm, this rule is routinely broken. An electron or a proton can encounter an energy barrier just like that hill, a wall of force it seemingly lacks the power to surmount. According to the old rules, it should be reflected back 100% of the time. Yet, there is a small but real probability that the particle will simply appear on the far side of the barrier. It does not go over the top, it does not go around the sides, it seemingly goes through it. The explanation lies in the fundamental fuzziness of the quantum world, governed by the uncertainty principle. A particle is not a tiny, hard marble with a perfectly defined location and trajectory. It is better described as a cloud of probabilities, a wave of potential spread out in space. This wave function does not stop abruptly at an energy barrier. It exponentially decays inside it like an echo fading in a tunnel. If the barrier is thin enough, this fading wave does not decay to zero before it reaches the other side. A tiny remnant of the particle's probability amplitude emerges from the barrier, meaning there is a chance, however small, that the particle will be found there. From our perspective, it has tunneled through. This process is not just a laboratory curiosity, it is essential for life itself. Inside the core of our sun, protons need to collide and fuse to release energy. But they are all positively charged and they repel each other fiercely. The electrical repulsion between them creates a monumental energy barrier. Classically, the temperatures in the sun's core are far too low for protons to have enough energy to overcome this barrier and get close enough to fuse. It is quantum tunneling that provides the answer. There is a small but statistically significant probability that some of these protons will tunnel through their mutual repulsive barrier, allowing fusion to occur and the sun to shine. Without this quantum cheat code, the stars would remain dark and cold. The same principle is harnessed in modern electronics, enabling the flash memory in your phone and the scanning tunneling microscopes that let us image individual atoms. Yet, for all its utility, the mechanism remains deeply puzzling. The particle does not literally bore a hole through the barrier. It exploits the inherent uncertainty of its own position, blurring the lines between here and there in a way that has no analogy in our macroscopic world. It challenges our most basic ideas about location, motion, and what it means for an object to travel from one point to another, forcing us to accept that at its most fundamental level, the universe operates on a principle of potential and probability, not on certain paths and solid walls. Our cosmic recipe book contains a fundamental error written in the very first elements. According to our most trusted models of the Big Bang, the universe's first few minutes were a frenetic nuclear forge, fusing protons and neutrons into the lightest elements. This process, known as Big Bang nucleosynthesis, should have left a specific, indelible signature across the cosmos, a primordial mix of hydrogen, helium, and a tiny trace of lithium. For hydrogen and helium, the predictions match the observations in ancient, pristine stars almost perfectly, but for that third element, the numbers fail completely. The oldest stars in our galaxy, which formed from the unpolluted gas of the early universe, consistently show only about 1/3 of the lithium that our Big Bang calculations insist should be there. Billions of years' worth of starlight confirm it. The lithium is missing. This is not a small accounting error. It is a glaring threefold discrepancy that has stubbornly resisted every attempt at a solution. For decades, cosmologists have refined their models, checking and rechecking the nuclear reaction rates and the density of the early cosmos, but the lithium problem refuses to vanish. It stands as a quiet, persistent crack in the foundation of our origin story. What could have consumed this primordial lithium? Perhaps unknown nuclear reactions occurred in that first fiery forge, pathways we have not yet discovered that destroyed the lithium as quickly as it formed. Or maybe the ancient stars themselves are the culprits, somehow dragging the lithium from their surfaces down into their cores where our telescopes cannot see it, though no conventional stellar model explains this adequately. More radically, could this missing element be a clue that the conditions in the first moments were not what we think? Perhaps the density of matter was different, or an unknown particle was present, influencing the nuclear reactions in a way we have not accounted for. The cosmological lithium problem is a humbling reminder that even our most successful cosmic stories, those that explain the abundance of everything else, can harbor a single, unresolved flaw that points toward a deeper, more complex truth waiting to be uncovered. Even our own cosmic inventory is shockingly incomplete. We have spent decades searching for the exotic substances of dark matter and dark energy, yet we cannot even account for all of the normal stuff, the atoms that make up every star, planet, and person. This is the mystery of the missing baryons, a cosmic census of the nearby universe, a grand tally of all the visible stars, the glowing gas within galaxies, and every detectable cloud reveals a startling shortfall. We can only find about half of the ordinary matter that our most trusted models insist must exist. These models, based on the pristine conditions of the Big Bang as recorded in the cosmic microwave background, give us a precise recipe for the universe. They tell us exactly how much normal, baryonic matter was forged in that first fiery moment. And yet, when we look around at the modern cosmos, nearly 50% of that expected matter is simply gone. It is not hiding as dark matter. This is the regular atoms that should be lighting up our telescopes. So where did it all go? Theoretical work points to a hauntingly beautiful solution, a ghostly web of matter known as the warm-hot intergalactic medium. Picture the universe's large-scale structure as a vast cosmic web, with galaxies strung along brilliant filaments like dew on a spider's silk. Theorists suggest that the missing baryons are not in the galaxies themselves, but in the spaces between, condensed into these immense, faint filaments of incredibly diffuse gas. This gas is so hot, heated to millions of degrees by the gravitational shocks of falling into these cosmic highways, that it does not emit visible light. Instead, it glows faintly in high-energy X-rays, a whisper of heat that is incredibly difficult to detect against the background roar of the universe. We have had tantalizing hints, brief absorptions of light from distant quasars that suggest this warm hot plasma is there, weaving through the emptiness. But directly mapping this hidden ocean of matter has proven to be one of observational astronomy's greatest challenges. This missing matter problem is a humbling reminder of our own blindness. We have mapped the grandest structures in the cosmos, yet we are missing the very threads that sew them together. It forces us to confront a universe where the majority of its normal atoms exist in a form we are only just learning to see, a faint, hot fog that represents the final frontier in our quest to simply find ourselves. Even our most precise cosmic measurements are now at war with each other. The universe appears to be expanding at two different speeds, and the discrepancy is tearing at the seams of our standard model of cosmology. This is the Hubble Tension, a stubborn conflict between how fast the cosmos was growing in its infancy and how fast it is flying apart today. For a century, we have known the universe is expanding, with galaxies receding from us at speeds proportional to their distance. The rate of this expansion is encapsulated in the Hubble constant, a single number that describes the current tempo of the cosmic symphony. The problem is we cannot agree on what that number is. One method uses the cosmic microwave background, the fossilized light from the Big Bang, as a pristine snapshot of the infant universe. By meticulously mapping the tiny temperature fluctuations in this afterglow, satellites like Planck can extrapolate forward through 13.8 billion years of cosmic evolution to predict what the expansion rate should be today. This is the ultimate top-down approach, starting with the universe's birth certificate and calculating what it must have become. The result is a specific, precise value for the Hubble constant. A separate, bottom-up approach measures the universe's current expansion directly. Astronomers use a cosmic distance ladder, calibrating the brightness of nearby Cepheid variable stars and Type Ia supernova in distant galaxies. These celestial mile markers allow us to gauge distances across vast stretches of space, and by comparing to the galaxy's recession speeds, measure the expansion rate right now in our cosmic neighborhood. The shocking revelation is that these two methods do not converge. They disagree by a small but statistically significant margin. The local, modern universe seems to be expanding about 10% faster than the early universe's blueprint says it should be. This is not a minor rounding error, it is a fundamental contradiction. If the local measurements are correct, then our extrapolation from the early universe is wrong, implying that some unknown ingredient or physical effect altered the expansion history after the cosmic microwave background was released. Perhaps dark energy is not constant but has been evolving in strength, or an unknown type of relativistic particle was flooding the early cosmos, changing its expansion dynamics. If the Planck measurement from the early universe is correct, then there must be a systematic error in our local distance measurements that we have not yet uncovered, a flaw in the rungs of our cosmic ladder that has persisted despite decades of refinement. The Hubble tension is more than a technical dispute. It is a direct challenge to the Lambda cold dark matter model, the foundational framework of modern cosmology. This model has been spectacularly successful at explaining the large-scale structure of the universe, but the Hubble tension suggests it might be missing a crucial piece of physics. Resolving this conflict may require us to rewrite the cosmic rulebook once again, introducing new forces, new particles, or a new understanding of dark energy to explain why the universe's past and present are telling two different stories about its ultimate fate. The final stop on our journey is a failure so profound it defies any sense of scale. Quantum field theory, our most successful framework for the subatomic world, makes a prediction about the energy of empty space. It calculates the vacuum should be brimming with a colossal power, a seething background hum from all those virtual particles flashing in and out of existence. The number it gives is not just large, it is monstrous. It suggests a vacuum energy density so immense that its gravitational effect should have torn the universe to shreds in the first fraction of a second after the Big Bang. The cosmos as we know it simply could not exist, yet here we are. When we measure the actual energy of the vacuum through the observed acceleration of the universe, the value we get is almost laughably small. It is not just a little bit off. The theoretical prediction is one followed by 120 zeros times larger than the observed reality. This is the vacuum catastrophe, the single worst prediction in the entire history of science. It is not a minor rounding error, it is a chasm of misunderstanding so vast our minds cannot truly grasp it. This discrepancy forces a brutal choice. Either our understanding of the quantum vacuum is fundamentally and catastrophically wrong, or our cosmological models for how that vacuum energy gravitates are missing something essential. Perhaps the infinite sums used in quantum field theory need a radical new approach, a way to cancel out these impossibly large energies that we have not yet discovered. Or maybe dark energy is not the cosmological constant after all, but something else entirely, like the dynamic field of quintessence that only mimics a faint vacuum energy. The vacuum catastrophe is the ultimate confrontation between the two most powerful theories ever devised, quantum mechanics and general relativity. It screams that we are missing a crucial piece of the puzzle, a principle that seamlessly connects the frenetic world of the quantum to the grand stage of the cosmos. Resolving this may require a revolution as profound as the ones ushered in by Newton and Einstein, pointing toward a new framework where the very concepts of nothing and everything are forever redefined. Confronted by these profound failures, our scientific story cannot simply end. It must evolve. To mend the torn rulebook of reality, physicists have been forced to dream in entirely new dimensions, crafting theoretical frameworks that sound more like myth than mathematics. String theory is one such grand ambition. It proposes that the fundamental constituents of the universe are not point-like particles, but unimaginably tiny, vibrating loops of energy. In this view, an electron is a string vibrating one way, a quark another, and the force of gravity yet another. This elegant idea naturally incorporates gravity into the quantum world and holds the potential to describe what happens at the singularity of a black hole or the first moment of the Big Bang. But the cost of this unity is steep. The mathematics of string theory only works if the universe has many more dimensions than the 4 we experience, perhaps 10 or even 26. These extra dimensions, the theory suggests, are curled up into spaces too small for us to perceive, like the intricate folds in a piece of fabric viewed from a distance. While it promises a theory of everything, string theory has so far struggled to make testable predictions that could move it from beautiful mathematics to confirmed physical law. Another profound approach, loop quantum gravity, takes a different path. Instead of altering the particles, it reimagines the very stage they perform on. This theory proposes that space itself is not a smooth, continuous backdrop, as Einstein described, but is woven from a fabric of finite, interlocking loops. Picture spacetime as a vast network of a billion tiny threads, a spin network where each intersection represents a tiny grain of space. This quantum of volume is the smallest possible piece of reality, meaning you cannot have half a unit of space. This granular structure could prevent the infinities that plague the centers of black holes and the Big Bang, offering a concrete picture of a universe that was not born from a singularity, but perhaps rebounded from a previous cosmic cycle. Yet this, too, remains a work in progress, a compelling sketch of a quantum universe that we cannot yet experimentally touch. Beyond these giants, even more radical ideas are taking root. Emergent gravity models suggest that gravity is not a fundamental force at all. What if the space-time curvature that holds planets in orbit and warps light around galaxies is not a primary feature of the cosmos, but an illusion? This perspective argues that gravity, and perhaps even space and time themselves, are emergent phenomena. They arise from something more basic, much like the temperature of a gas emerges from the collective jostling of countless molecules. In this view, the smooth fabric of space-time is a kind of hologram, projected upward from a vast network of quantum information entangled across the universe. This could provide a stunning resolution to the black hole information paradox, as the information of what falls in would never truly enter the black hole, but would be encoded on its two-dimensional surface. Each of these frameworks offers a unique key to some of our 30 cosmic mysteries, yet each key seems to open a door into a room filled with new, even more perplexing questions. String theory gives us unity but demands hidden dimensions. Loop quantum gravity gives us a granular space but has yet to fully incorporate the other forces. Emergent gravity reframes our entire reality but challenges our most intuitive concepts of what is real. This vibrant, sometimes contentious, proliferation of ideas is not a sign of science failing. It is the sound of science straining at its limits, a chorus of brilliant minds refusing to accept that the universe's deepest secrets are forever beyond